I have to admit, I wouldn't describe myself necessarily as a data scientist all that often. Depending on who you talk to in AIB, I'm voraciously a data scientist, financial analyst, data analyst, or sometimes also known as that guy who spends ages staring at a screen with little green roundels displaying something. It's just something is going on, but we're not quite sure what, so we better leave him to it. The best sort of position to be in, I guess. Can everyone hear me okay? All right, fantastic. If you don't, by the way, raise your hand during this. I do have a terrible habit of moving away from a microphone. So I guess I'll just go straight into it. And thank you, by the way, for the previous talk about functional programming. You pulled in quite a decent few people. I wasn't expecting many people to turn up for this, so it's quite nice. Actually, now we're on the topic, just before we go into the topic itself. So who here actually did computer science before their career? Okay, so decent few. Did you cover functional programming principles during that, or did you have at least some introduction to them? Like, did anything at all? No? Okay. Oh, there was one down there. Where did you go, can I ask? UCD. Okay. Is anyone else here UCD, or? Okay, no, just a minority one. I'm UCD as well, but I didn't do computer science. Unfortunately, I came to it out of interest. So, no, but it kind of goes into what I'll be discussing a little bit as well, which is that it's kind of even suggested by the topic now, as we'll see as well. Sometimes, lately, you see all these sort of courses online. I presume you'll see tons of them. They're in Python 24 hours. Everything to do with Python, basically, you can learn in a couple of days or whatever it is they go on. And it's led to kind of an interesting effect, I think, on the industry. And I say that as someone who came into this myself a few years ago. It's interesting to see the quality, the variable quality you get associated with teaching Python. Almost universally, even if they've taught it as a later language, they don't seem to have a lot of ideas of the understanding of principles of computing. My God, there's still people arriving. I'm starting to get intimidated now. Same. But, sorry, so I'll start this off actually with two little apologies. One, I'm going to confess in advance, yes, you may throw stuff at me. I'm using Windows 7. And that is for a very good reason. That is because as an educator, you are expected, perhaps they hope that you know almost everything. And nothing shatters that myth faster than having a laptop running Ubuntu that you go to do a presentation on, and immediately you get a message saying, sorry, the graphics drivers have uninstalled themselves. Will you spend the next 10 to 15 minutes actually Googling for them, reinstalling them before you continue your presentation? So hopefully you're okay with that. And I can tell there's at least one or two people here who've had that happen to them before. It happens to everyone. And secondly is, I suppose, it's something of a slightly misleading title as well, because it's called Programming and Poking Some Experiences. And the thing is, Python itself, although I'll be explaining quite a lot in this, and I actually use it as the primary programming language, it's my first programming language as well, funnily enough. This could be easily have been about almost any other language as well that I'll cover in this. A bit of C, some Scheme, which functional programming chapter will absolutely love, to the Lisp. And a bit of Lua as well, which is a little bit like Python as well, but it's a smaller standard library. It's a bit more used for network configuration and game scripting. And I guess what I'm trying to say is, you could say that it's not purely about Python. I'll be talking more about concepts. It'll be more about anecdotes, rather than necessarily having the absolutely hard data of this approach is better than this approach that you'll see comparison Python to C or Python to some other language. So I hope you don't mind seeing that. If so, don't worry, I won't be offended if you leave. I almost half expected it. So we'll jump right into it then. As I was introduced there, I work in AIB, data scientist, but I also have been teaching the past year or so introductory programming. Usually it's introductory programming, usually with data analytics, funnily enough. I'll be formally teaching it now in an actual proper teaching position at Dublin Business School next semester. So hopefully none of my students of the time will watch this and realize, hang on a sec, he's given us several assignments that are based in this as well, that you've been discussing. So no, of course there isn't. Okay, so we'll jump into them. So what actually prompted me to do this lecture, it's not related to the title, we'll get to the title in a minute, was, funnily enough, actually this headline that came from 2014, I believe it was, from the Association of Computing Machinery, one of the oldest associations in the world to do with computers, back in 1947. And their headline was essentially that, as you can read here, at that time Python had become formally the most used language in an introductory to computing courses in the United States universities. And indeed, they had pretty much said as well, many other places across the world. And now that's got many caveats to it. Yes, it's used in many courses. Some of them are very good quality courses, some of them are debatable quality, and some of them are, well, let me just put it to you this way. There's a reason for the origin of this cartoon. Some people might agree with it, some people might not, I don't know. Some people, there seems to be quite a bit of degree of agreement with it, depending on where you go. I'd probably assign myself the second category, to be honest, the bottom one. At times, there's nothing that makes you feel less like you know Python when you realize, oh damn, I could have used something very simple in a looping construct there instead of using map in a really complicated sort of way. But it's kind of unfortunate as well because a lot of the people who've been coming in, yeah, some of them have been going in because they've been hearing, oh, it's great to get into programming, you learn Python, you'll end up, with a six-figure job in Google or whatever. But also, a lot of them I've observed as well, are actually coming from different backgrounds that are intending to use, maybe not necessarily Python, but to understand some sort of computational way of thinking, to how they can use programming, maybe Python, maybe something else, in their day-to-day activities. And the rough breakdown, as Susan was discussing in the very beginning talk that we had here, introducing Pycon, this is only a fairly small set. It's about, I'd say, a total of 35 individuals spread over quite a period of time. So with one big class and then a few other little individuals scattered here and there. So try to take it as that rather than a very heavy scientific study. I'd say roughly about 50% of them came from some sort of financial or insurance or some sort of background like that. You get what I mean, right? So they would have had some experience already. They have some math knowledge, usually math knowledge. They're usually reasonably good at it. They have some experience usually using Excel, that thing we shall not speak its name of again, according to some people. Some of them have had Visual Basic. Yes, I know. I shouldn't say that because I've had to do Visual Basic as well, so I don't know why I'm being so superior about that. But a large proportion of those who come in are actually from other backgrounds as well, like arts graduates, for example, who aren't necessarily even lured in by that idea of, the big paying job or whatever it is, but simply because it's sort of an interesting field in a way. It's those years of people trying to constantly get people to go into, the STEM shortage and trying to go into that field. And some of them develop a love of it, some of them don't. Almost universally, and we'll see this again later on, most of them don't particularly like maths. They may not necessarily actively hate it, but for them it ends at the leaving cert, or when you leave normal school and you go into university. They will do quite a bit to try and avoid doing all the most simple mathematical operations. And I can't say I blame them, but we'll get on to that in a bit. But there are sound structural reasons for using Python, I feel. And I'm certainly not the only one to think so. And here we get to the actual quote that started this title. The one that actually really got me thinking about how would I frame this sort of, what I'd experienced. This is from Gerry Sussman, who co-produced, I should say, probably what could be called the first functional programming course, and indeed probably one of the greatest introduction programming courses of all time, or at least that's certainly the debate that rages constantly online anytime anyone brings up anything to do with him or anything to do with MIT, etc. So back in the 1970s, they decided, back then there wasn't a computer science as such. Hell, software engineering was only coined as a term back in about 1968 or thereabouts. But back in the 70s, there was a debate about how exactly, because it was going to be taught as part of electrical engineering, how exactly would you teach computer science in a way? And what Sussman and a few others came up with was this sort of language that's almost based on mathematics at its heart, which is that you could use a few little notations like define, for example, to define a procedure or function or whatever. And with a few like that, you could represent a language with just a few little notations, fully, Turing complete. I don't want to say Turing complete, but you know what I mean, a fully useful programming language. And it actually has gone on quite a bit since then. In fact, it lasted for quite a long time. It was taught until about 2009, from when it actually began, about 1984, thereabouts, I think it was. Sometime in the 1980s, anyway. There are videos of the class online. I do encourage you to watch them, by the way. It's quite interesting. But around 2009 or thereabouts, there had been quite a debate for quite a while in MIT. Was the course load too hard? And if you do go into a bit greater depth, you can see sometimes people post blog posts somewhere from that period, or as sort of retrospects in a way, because this course wasn't just restricted to MIT. The book, which is basically a wizard who's holding out this sort of hand conjuring some sort of magic, which is meant to represent programming, as someone said there earlier on, was used in various forms throughout various universities. Some of them still do use it, but it was quite a big thing. But the thing was as well, they had quite substantial dropout rates, and while the graduates who did come in understood a lot of the foundations of programming, they were too few in number in a way. Remember as well, this is coming up to about 2000 as well. There's quite a big demand for programmers when this debate first started. And then the dot-com crash happened, of course, and I think the introductory to computer science course dropped to about 40% of what it had been previously in 1 year. So that should give you some idea of the dramatic drop in figures. Other places had exactly the same figures. And there was a constant demand saying, perhaps this is too tough. We are teaching very much that this is a functional programming language. Perhaps we should do it in a way that's more useful. And eventually, after many years, the new board decided on a new course, which is going to be used purely in Python. It's still there today. There are other things as well that you study after that, by the way. It's not just purely Python used for everything. Python is simply the introductory language and used in a few more difficult courses, as we'll see a little bit. But what really interested me was this quote from Sussman, which you can read there now, and I'll read it out myself anyway, just because I think it's interesting. This is a quote from when they'd announced that this was going to turn to Python. So they felt that the SIP, Structure and Interpretation of Computer Programs, was the name of the original course, and the book, by the way, for those of you who were wondering, was no longer preparing engineers for what engineering is like today. Sussman said that in the 80s and 90s, engineers built complex systems by combining simple and well-understood parts, modularity perhaps. The goal of SIP was to provide the abstraction language for reasoning about such systems, i.e. they were fairly small, everyone could kind of understand what was going on in a way, because you were so comparatively close to the metal, I guess you could say. There was fairly little in the way of heavy-duty abstraction. You built abstractions yourself upon very loose abstractions to begin with. But today this is no longer the case. Sussman pointed out the engineers now routinely write code for complicated hardware they don't fully understand and often can't understand. The same is true of the software level, since programming environments consist of gigantic libraries. I'm wearing a TensorFlow t-shirt, I dare say you'll agree with that. And with enormous functionality. According to Sussman, his students spent most of their time reading manuals for those libraries to figure out how to stitch them together to get a job done. He said that programming today is more like a science. You grab this piece of library and you poke at it. You write programs to poke it and see what it does. And you say, can I tweak it to do the thing I want? This analysis by synthesis is the view of SIP, where you build a larger system out of smaller, simple parts, became irrelevant. And nowadays, as the little bit of the article at the bottom here, we do programming by poking effectively in Sussman's view. Now, what exactly he meant by that was the subject of kind of a quite substantial debate online in various forums. Some took it as an implicit criticism, as indeed it possibly was, because he had been there at the electrical engineering side. He had developed the original course, and his criticism was that in a way Python was too abstract. It wasn't providing the fundamental knowledge of how exactly computers worked. Things like memory allocation, for example, how exactly the things like linked lists work, for example. We just literally create a list in Python, but there's actually more nuance to it than that. Various little operations like that. But also as well, how to say it? Sussman was also acknowledging a reality. The programming had fundamentally changed. Most engineers nowadays didn't work in C at that time anyway. They still don't work nowadays, obviously, in it. But JavaScript and other libraries, essentially you stitch together other programming languages, other programming constructs that were already done for you by someone else. You might have even made them yourself, perhaps, but you made them in a different language. You didn't have to go such fine level detail. And moving on from him now, I'm going to talk about my own experiences in using Python and how exactly it interacts with what I think is sort of the inability to teach some aspects of computational thinking or computer science with it. So Python's effectiveness as a communication tool is the first thing, and probably the one that everyone would immediately guess anyway, because of its, the cleanness of the syntax. Anyone who's had experience with another language will probably agree with that. Python's used in improving mathematical ability. Once again, you'll see throughout this, I occasionally say, we'll come back to a little bit of this now in a moment. That means that we're coming up towards the final bit of it, which means some problems potentially in using Python, because not everything is nice. Just because it improves something doesn't mean necessarily that it's not without its drawbacks. Potential projects that can be much easier to make in Python, thus actually deliver something physical or something, it has a tangible goal they actually want to interact with our potential students, in which case, obviously they'll be more inclined to take up the keyboard. Take up the keyboard, as it were. And also, of course, that thing that probably everyone is actually really here to hear is some problems with using Python. So, actually, funnily enough, Python is intended almost from the get-go to be a language that could be taught. It was descended from a language that Guido had worked on in the 1980s called ABC, which, as the name might suggest, was actually intended purely for teaching. And it had a similar sort of syntax. It was very clear. There weren't really any use of brackets, for example. It was very structured that you used a lot of capital letters, for example, to define very obvious procedures. If you look up some of the, like ALGOL60A, for example, you'll get a pretty good idea. It wasn't a huge language, but it worked comparatively well for what it did. And its syntax was quite close to what we have as Python today. And Python itself started out as a idea that obviously you should have something that's much cleaner, much simpler to read. Maybe you can sacrifice some of its ability to do low-level stuff for that. That's what the thinking was anyway. But the whole point of it is that it's very easy to communicate with in a sense. It's easy to break down a problem into something that you can write there and then. You don't have to worry about, where exactly the order the brackets come, what exactly should be the name of this built-in function I'm calling, etc. And funny enough, actually, one of the people who is quote on Python actually made it in. This presentation was originally about 3 times as long, with lots of quotes of inspirations from various people, which basically had nothing to do in reality with Python other than just saying it was very nice to work with. But one of those who did, funny enough, was Peter Norvig, who's one of the heads of research. He was head of research, at Google. And his own quote here is given on, I think it was an article on Hacker News about why exactly he had rewritten his Introduction to AI course using Python, or why he had rewritten some of the pseudocode in doing so. And essentially his point was, you'll be able to read it up there, I'm not going to go out of the way to read it, was that essentially it was much easier to frame your thoughts in an actual readable way to the computer using Python. The syntax lent itself very well to doing so. It was a very effective communication tool for when you needed to teach people concepts that they then needed to be able to translate into something else. By contrast, Lisp, which is what he originally had written it in, is quite a confusing language with lots of little brackets, as we'll see. And likewise, it was also missing quite a lot of stuff as well. Don't forget that when he wrote this, it was actually back in the 1980s, and debatably even predated that. So there had been quite an advance since then. And obviously, of course, you have now so many libraries that actually do embody so many things that you would have had to build from scratch back then to do so. Funnily enough as well, he thought that Lisp actually had the edge for certain larger projects, especially for speed. We'll obviously hear of that towards the end. I think everyone knows Python's speed is quite legendary in terms of slowness. But we'll come back to that anyway later on. But I thought I'd do a quick comparison just to give you an idea of why that is. So, funnily enough, actually, when I was teaching this, I kind of expected that everyone would get Python comparatively easily compared to, other languages that they might have been potentially introduced to at some point. And almost universally, actually, the people who worked with finance or had some sort of Excel experience, basically, or some Visual Basic experience, actually got Scheme, funnily enough, much better than they did Python initially. I presume because of the sheer amount of brackets. There's a very famous magazine cover somewhere where essentially all the statements terminate with brackets, but the problem is you have multiple nested brackets at the end of a very long expression. And there's a magazine cover somewhere from a computing magazine, I think in the 1980s, where astronauts come to Earth in the distant future to discover that the world has been destroyed, and they come upon this great stone tablet that describes a computer program that presumably describes something great about humanity, and they get to the final stone first, and they discover it's just literally end brackets constantly. Because that was the way you had to end it. It was undoubtedly very difficult to understand, but I dare say if you've worked with programming in Excel, you probably have seen multiple nested if statements that have constantly ended in about, I think, half a page of end brackets possibly. I certainly have anyway. But then again, I do work in finance. It's a wonderful thing. Nothing will quite ruin your day as much as seeing about 40 nested if statements and Visual Basic code all crammed into one little tiny cell. I think everyone here has had that. But funnily enough, and you can see a comparison here with C and Lua as well, which is quite similar to Python in some ways. And the main reason I mentioned Lua is simply because not only because it is slightly similar to Python, but also because at one point as well, as we'll get onto a little bit when I talk about mathematical ability, I actually did use it alongside Python to try and reconstruct a Python originated project. And exactly how successful that was, we'll see in a little bit. But surprisingly enough, actually, it was the ones who you could possibly think of as the thinkers in a way. The ones like English majors, for example. They were the ones actually who got Python quite well in a way. And I always wondered exactly why that was. And one of them explained it to me that effectively it was, as they said, sort of pseudocode, but it was also because it was very easy. Once you had an idea of how to solve a problem in your head, it was easy enough to translate that into something that was on the screen. It didn't necessarily work immediately. Christ, I wish my code would work immediately. But it often worked well enough they could build up something too, and they could usually end up with some sort of bloody mess of code. Thankfully, I didn't have to teach them how to do it exceptionally well. That was on the next semester's module. I did do a little bit, but not too much, thankfully. But they ended up with something that did actually work in the end, which surprised them greatly, surprised me greatly as well at times. But it lent itself very well to, once they had finally solved that issue, to expressing it in some way into code that they could actually get the computer to run. And as I said, surprisingly enough, the financial people didn't get this too well. They did eventually, usually, I presume because they've had some experience in doing such operations. And funnily enough, actually, this trade-off that you see between like C, for example, there, and Scheme and Python is a little bit more obvious, I think, when we get to looping constructs. So in Python, it's quite a bit more simple. We'll see it here. In fact, literally almost anything could be iterated over in a way once it consists of more than one item. It could be a string, could be a list of items, whatever you fancy. Scheme, strangely enough, doesn't actually have a looping construct. It's almost like a pure functional programming language. You do have to use recursion, hence why it's not a direct comparison there for the exact same program. It just simply wouldn't have been possible. And for C there, well, I think that mess kind of speaks for itself in a way. In my defense, that was what everyone I asked when I asked for an opinion on this presentation said was, yes, this is probably the simplest C example for a loop you can give, relatively speaking anyway. But you get an idea. And funnily enough, actually, this also emphasizes another way that Python was intended to be quite a good communication tool, or how it ends up being quite a good communication tool by design. Because in the early days of it, funnily enough, the column at the end of the for loop was not actually needed by the parser when Guido was developing this. He did an initial test and discovered that you had the indentation then, that was a very early part of it, but there was no terminating colon, so users got very confused as to where exactly their statement ended, and it got onto the actual body of the code to be executed within the loop. And so that was added as a mandatory piece later on. And funnily enough, actually talking about schemes and recursion there, one of the things that I was actually talking about earlier on, just before the presentation began, with my colleague there, who went into the functional programming presentation, was it's quite difficult to actually do proper functional programming in Python. It's very difficult to express a lot of ideas because it's not designed for that. And indeed, it was one of the battles that's been sort of raging for many years in Python was how functional can you actually make it? Guido never intended it to be a functional programming language, and he fought all attempts to do so. Oh, I'm so flattered. If only. But he fought all attempts, really reasonably anyway, to try and introduce it, more functional aspects into Python. And it's actually quite strange in a way, relating back to what I said there about computer science, that we still don't really learn outside of one or two courses functional aspects when you consider how much of modern computing is built upon distributed processing in a way. We kind of rely on AWS or other cloud systems to actually do so. But we don't really understand how that works in many places. We just sort of dump a massive query in SQL, for example, into SQL Server or whatever it is, and it just runs, and by magic, everything runs absolutely fantastically. Unless, of course, you're the database administrator, in which case you do have to worry about that sort of stuff. But thankfully, that's not for the majority of people. Otherwise, I dare say we'd be having a very different conversation. The strange thing is as well, actually, when I was teaching, I'll mention this now, I was going to mention it a little later on because we're on loops as it is right now. Python's cleanness, as I think Suzanne was mentioning, encourages sort of laziness in a way, and we'll be coming to this again later on as well, which is that the minute that you had some sort of thing that worked well enough, they tended to stick with that. And one example of this was, for example, say if we didn't want to iterate over fruits directly, you forgot about it. What might you use instead? Well, you might use, for the length of fruits, it's like just going to be 3 because there's 3 items in it. So for that amount, and print, well, what would you print in that case? Well, you print fruit, and then you use your array. This is an example that was actually given to me, by the way, by someone who I'd brought up to the whiteboard to do almost exactly the same thing. It was actually like 5 characters long, but you get the idea. So they did the for loop. They used length of whatever the list was, the length of list, and then said for each time you need to print that subject, print the individual character where I is in that list, and an individual number in the array of that list, if you were. And it boggled my mind because this is such a inefficient way to do it. You have to call len of that object multiple times to check, when you're doing the for loop, is this condition still being met? It was completely foreign to them that you might assign this to some other variable beforehand and then just, do it that way. Or perhaps even just, iterate directly over the list. And I can't say I necessarily blame those, but there were some people who actually had programming experience for whom this didn't necessarily occur either. I don't mean like Visual Basic or VBA. One of them had actually been quite a long time Ruby programmer, surprisingly enough. There was also a chap who'd had quite extensive experience working in C, and he'd also done a fair amount of work in SQL. So it wasn't just, people who had no programming language to begin with. It was something that Python almost seemed to inspire them in a way, which is that it works well enough. Let's leave it at that. We don't really care too much about speed. And even at my introductory level, when I wasn't supposed to care too much about speed, that was supposed to be done in the next module in the case of the class I was actually teaching. Even I recognized, no, this is something that had to be corrected, and multiple attempts were frequently put in to try and do so. And funny enough, actually, it makes up the final lesson of what I actually would teach them, half and half. We'll see the other half now of what exactly that lesson is. The first half of it is how to write another programming language in Python. This is almost a tutorial in a way. It's given by Peter Norvig on his own website. It's very interesting because he goes into the basics of how programming languages actually work, and you get some ideas that I don't think Python expresses very well as how you can speed up some languages far more. He's like using map, for example, instead of just directly iterating over something, trying to apply a function. Map makes it a fair bit faster, and also the use of built-in functions as well, because obviously a function written in Python is never going to be as fast as a function written in C, all things considered. Well, debating on the internal structure, but you get what I mean. But the second half of it was going to be, and it's probably going to be again now when I end up teaching properly next semester, it was an optimization sort of module. And I don't mean optimization as in, okay, this is how you write, this is how you optimize stuff. It was a module literally saying don't use the length function in a statement where it's going to be called repeatedly when you can literally do that, assigning it to one variable. And perhaps that's me having some experience in the field practically as well, but at the same time it was also a very visible lesson in a way. And one I didn't expect myself, because when I did it, I'm sure, when I learned Python, I did something similar as well, but I also learned very quickly that, you can make little cheats here and there to try and speed this up a little bit. Not a massive amount, but it makes an effect over a large data set or something similar. And it just boggled my mind that even formerly skilled programmers would tend to resort to this sort of thing. It was bizarre, and one that ultimately I think I'd like to hope maybe my former students, if they're watching this on YouTube, or if they magically hear of this somehow, will let me know if they actually gained something from this. Hopefully they did. Now I will also stress as well, by the way, that programming language is freely available online. I have put a little thing down there if you want to find it. You'll find it very easily enough. It is well worth a shot, written in Python 3. It does need a little bit of changing though before you can actually run it directly. And it's well worth an idea because, as I said, it does express multiple concepts that Python I don't think necessarily covers very well, or it's very difficult to do so with Python. For example, the nature in which you actually evaluate, or the computer evaluates operations. Why does Go actually, for a certain operation unless it's in brackets before another operation? So, I love this little guy, by the way. I made a demo of this presentation to someone, and they literally said, "Oh, I love the little Viking." I can't remember what else happened in the presentation, but that was great. So that was a great blow to my ego. Or perhaps I should put it another way. No, that's okay. So one of perhaps the biggest surprises, because I hadn't taught my initial class that I taught was purely in Python with a little bit of coming to scheme at the end because of the way that it was structured to have a scheme sort of interpreter built in Python at the end of it. And one of the surprises me, I suppose, even though I learned it as my own first language, was how much more intuitive Python made maths operations for most students. And I don't necessarily mean that, suddenly they could add very quickly or divide very quickly or something like that. But it's more that more complex formulae were something that they could render down more easily. They didn't necessarily understand why exactly they had to get a probability of something, or like how to do that from first principles. But they understood if they had some value that stood for a probability, all probabilities having to add to 1, for example, that they could write this equation as was expressed in mathematics, and they could do so reasonably well in a way they could understand, in a way that I suppose they made more sense, and they could debug it a little bit easier, which is something that I really had not expected, possibly also because, frankly, I have done some work in MATLAB before, which is a more pure mathematical language, but is hell to debug, as I dare say most people will attest to if they've ever had to work in it. So just to give one example, this is actually one that, funnily enough, when I was actually being taught Python, this was one of the advanced items. This one was actually done as sort of like a weekend one, so not the whole class turned up. A few people did, about half the people who'd been working in finance or other analytics fields or had previous experience turned up, and the rest of them were from a variety of other backgrounds that were non-technical. But this one actually comes from, I think it's a Facebook hackathon idea, which is that you have this sort of enemy you need to do damage to, and you need to find the best way to balance the amount of warriors you have with the amount of shields that you need as well. And the story goes that each warrior costs 5 points to buy and inflicts 1 point of damage for each turn they get. Now you can protect all warriors with just one shield. One shield costs 1 point. And that shield will protect them for 1 round, which means they can inflict another round of damage. So say you have 2 warriors, you have 1 shield. Well, those 2 warriors will inflict 2 points of damage in the first turn. The shields will be defeated, but they'll still be able to inflict another 2 points before they're killed for the next round. So that's 4 points of damage. And the point was, well, if you have 5,000 points overall to spend, how can you optimize this best to do the most damage to your enemy? Now, obviously, there's a lot of other ways you can do this as well. It's an optimization problem in a way. And it's one of those problems where it's very good, a good way to discover those who are capable of thinking in a very computational way, or even just simply translating a problem that's actually quite, I suppose you say mathematically based, into more plain text language and then converting that into computer code. And surprisingly enough, actually, when I prompting, 2 people actually came up with the answer almost immediately, which is basically a very for loop in a way. It's the simplest way to do it. You say, okay, if you have 5,000 points, okay, let's start off with all the warriors we can buy and 1 shield, and then gradually increase the number of shields we make and decrease the warriors in ratio and find out where the maximum value is. And surprisingly enough, 2 people actually out of, I think it was the 12 people who were there, actually came up with that pretty much immediately. And they hadn't had experience with this beforehand. Python made it much easier for them to implement that code, and a few others fiddled around with it a bit as well. They didn't necessarily get immediately why it was so important. Once they did so, they were very easily able to translate that into Python code, and immediately it was done. And I say it quite happily that most of them had it solved in pseudocode, and also were working on another project related to this at the same time within about 20 minutes. So that was good for me, especially since I was only doing this as one of my first after-school lessons, and it was a great, boost to me that the challenge I had actually assigned had been solved in relatively simple time, but was an actual challenge. Very nice indeed. So I'll get on to actually a more complicated one now, and this is one that was purely a side quest, I guess you could say. It was actually done originally for friends of mine who were also taking this sort of class. We were doing it almost more like cooperative. This is going to be done in C, and this is far more complicated. This is related to visual recognition. And funny enough, a few of the finance guys turned up as well, actually, for this as well. And Viola Jones is kind of an awkward one to try and explain. I've posted a link below to Computer Vol, which is a YouTube channel that does this sort of explanation. And it's well worth watching if you do want to. It's very good. But the idea is basically that this is before deep learning had made its big impact on facial recognition. And the idea was that faces have certain sort of areas that, regardless of what angle you view them from, are almost sort of going to have the same thing, i.e. we usually have this broad expansive forehead above this sort of dark area that represents our eyes. And the point of it was that by analysing just a few areas to get a few different sort of points that are roughly in like statistical size of one another, or like have some sort of meaning that correspond to this dark area into this expansive white area and so whatnot, or a brighter area, you can get a pretty good guess, like 99% of the time, that this is going to be a face. And there's all sorts of stuff about how difficult this can be to do on a very large picture. Once again, I do recommend the Computer File video. They do explain a great way to try and optimize this. But rather surprisingly enough, none of the people who actually came into the room who got together to do this algorithm for just a little simple test had actually done this before. And yet they were able to get it by literally watching a YouTube video and then doing the pseudocode directly into Python. Now, it didn't work flawlessly. There were some issues. It took quite a while to fix it. And there is a little element of machine learning in it as well. So obviously you have that whole sort of thing to deal with as well, which is quite well beyond introductory programming to begin with. But it was interesting to see exactly how there was no code whatsoever in the video that did the introduction for this. And in the first article we looked at as well, there was no code either. And so they had originally tried implementing this a bit in C because they thought, oh God, it's a massive pixel set. There's 3 values for every pixel in this, and it's a 2 million megapixel image. How long will it take to compute? But no, surprisingly enough, Python lent itself not only very well to expressing the concept, but also to expressing the idea they had about how you could optimize it as well. And I didn't actually expect that, because Python is not a language that really does matrix operations very simply. You have to, NumPy, its library, does that much better. But it made it very intuitive, and surprisingly enough, actually, it worked rather well. I wouldn't say it was it wasn't absolutely flawless. It was a bit slow, but it worked surprisingly well. And so that was, excuse me. God, it's only a few minutes in and I'm already dying of sore throat. But it made it much more interesting. And it's one of those practical things you could implement. Most people, if you brought them into a room, okay, in this case, you'd have to have at least a few lessons in Python, a bit in maths perhaps, to understand why this is so important. But at the same time, it is comparatively simple enough that someone could do it perhaps in their first year at a college like UCD perhaps, or perhaps a more intensive course could be done in a shorter period of time. And now we'll go back on to a slightly more statistical problem. So this is actually one that, funnily enough, I was actually working on. This was one that I brought into the class one day, just for the hell of it. And this was because I was reading that book, Bayesian Methods for Hackers. Yes, I know, you really shouldn't be introducing this sort of things to a class, but in my defense, about half of them had some experience with statistical stuff or math stuff before, so I was feeling confident. And indeed, they did get it in the end. And also because there was a maths course being taught at the same time that was also bringing this up, so I was helping them effectively cheat in that class as well. Because they all got the exact same answer, which was also, by sheer coincidence, the answer that was in the book that they were supposed to be reading with this question in it. So the idea goes back to the Second World War, and it's a problem that, to be honest, I didn't actually get myself initially, which is that, say, for example, you have production numbers on a number of tanks that have been captured, as indeed the British did during the Second World War. They captured a number of German tanks, and they wanted to estimate roughly each month how much the German industry were producing. And you can actually do this, funnily enough, using the serial numbers, presuming that they are consecutive, i.e., number 100 was built after number 20, for example. You can assume that going forward. It's how exactly can you use that, perhaps, to guess the total amount procured? There's a couple of numbers here. So 432, yada yada yada, all the way down there. Well, funnily enough, and I won't go into too much about how exactly this is done. Excuse me. The way to do so is actually a very simple statistical method where basically you take all the numbers individually, you count the number of times it occurs, and then you sort of run a probability distribution based on that. Well, it's a little more than that, but you get the idea. And surprisingly enough, this actually matched very well with what they'd been taught to statistics at the time as well. They'd been taught a bit of probability up to that point. In the case of the financial people, they already knew some of it anyway, they had to do so. And there wasn't much complicated maths doing so, it was just simply chaining operations together. And remarkably, actually, they did get this reasonably well. In fact, this is actually similar code to what someone came up with as, this was later on, by the way. This wasn't during the class itself, this was much later on. And this isn't my code, this is just very similar. I won't use his code here because I don't have his permission to potentially do so. He did say it was fine, but I couldn't find his code again, so I'm sorry, John. I have used someone else's code, but it's very similar to yours. But in this case, this is a slightly different version of it that uses different distribution of numbers. And I'd say it's probably a bit difficult to exactly understand what is happening there in a way. But I like the very absolute cleanness of it as well, and the way that it was easy enough to implement in that way. You could directly translate it from a statistical idea or a mathematical idea into code quite reasonably so. And I won't say necessarily that they had this idea of how they could apply this to other stuff, which is something we'll come to in the drawbacks bit of it. But they got the idea about why exactly roughly this worked in this way, and they were able to implement it from not having been given a code description line by line for doing so. And that seems kind of at odds with what I was saying earlier about having to, almost handhold them in a way through certain things. But the idea was there, and surprisingly enough, they did get it. And I think Python, remarkably enough, considering this is a Markov chain Monte Carlo method, was actually quite impressive, to be honest. They were helped, by the way, by someone who did actually know maths quite a bit, but at the same time, that is quite impressive considering he had no programming experience before this. And just in case you're wondering, by the way, how does this compare to something else, this is essentially the same thing in Visual Basic. Yes, my eyes burn looking at it. Let's get on to the next one. And this is, by the way, the results of that statistical method when run during the actual Second World War. The intelligence estimate versus the statistical estimate versus the actual production figures for that period. And I think you get a pretty good idea. They were slightly off, but they were pretty good. If you'd like a more modern example, by the way, Bloomberg have something that's still up at the moment, actually, a graph online about the number of Model 3s that Tesla have been producing over a certain period of time. And that goes by the VIN numbers that have been registered with the Department of Motor Vehicles in America. And theirs actually uses the exact same method as this, and that is actually still being updated. It's still, I don't think it's quite real time, but you get what I mean. It's still there, it's still being updated regularly, and it uses the same method as this with much nicer charting than anything I could potentially do. And it's one of those examples, again, I think, of how Python can be used for something potentially actually useful. I mean, I don't expect them to necessarily do heavy statistical stuff in whatever they were doing. I made that very clear to them, in fact, when one of them protested saying, how exactly will we use this? But the idea was that, this is something that you might not necessarily have thought about, and I'm sure you could apply it somewhere else as well. After all, Bloomberg could find a way for it, and if other places could find ways to use something similar, I'm sure they can too. And also because it was a good way to integrate with their maths lessons at the same time. One of the things I do like about Python, and one of the things I do try to emphasize as well, because of their dislike generally of maths. And so we get on to the practical projects. And so, funnily enough, actually, I think probably the thing I've heard constantly about Python is its fantastic library support. Okay. It's fantastic library support. And you can see a whole bunch of them here. OpenCV is the image analysis library. And Python lends itself very, very well to doing a lot of practical projects, some of them more advanced than others. This is one actually that was proposed that's based off a practical subject somewhere else. Someone got an iPad effectively and did deep learning, used a framework for machine learning, and used Python, obviously, to build sort of a Pokedex as a virtual app. And this is actually a project you can follow online. I'm not, unfortunately enough, the one implementing something similar to it. It was just simply an idea. And I do actually believe there's an AI course that'll be is in development at the moment that might use something similar to it. Likewise, it's also very good for robotics. This is on the left-hand side here, you'll see a rover built by the Jet Propulsion Labs. It's a few more minutes. Okay, I'll be nearly done now. Is a rover built by the Jet Propulsion Labs in NASA. This uses Python code. This is also if you can literally buy off the shelf. And likewise, there's a programmable drone as well that also makes use of a Python API. And I am experienced with the robotics part of it, but other people I know as well have explained to me anyway, that they found the robotics bit in particular was very well suited to using Python. It made it very simple, it made it very understandable. The mathematical methods involved in, say, doing pathfinding were a lot more intuitive in Python, or at least that's what they claim. I'm going to have to go with that, unfortunately. So we'll get close now to the wrapping up stage and going to the bit where I know everyone really wanted to hear. What's the problem with Python? Well, there's a couple of different ones. One, comprehension did not necessarily equal understanding of all the material they were being given. As I sort of hinted at during the World War II tank thing there, they understood the general equation, but they didn't necessarily understand why exactly they were doing what they were doing in every respect. And when I asked them to do a version of it that required a second series of serial numbers, it was actually correct. It was based on the wheel patterns. This is based on another real world problem. They floundered quite heavily, to say the least. And that was also the case, and I'm told this is the case as well by other people who've worked in the field longer than I have, that Python seems to encourage a sort of hand-holding in a way, and it's very odd. They don't tend to, they have all these interesting projects online. They won't necessarily even go out of the way to Google things, perhaps, as to why exactly something's wrong. There's a tendency to sort of say, okay, compiler error, does this work, no, okay, don't understand. And it's kind of annoying. And another thing that I had intended to do a bit more code comparison during this, but the sheer length of it kind of went against that, was I think probably the most famous thing is to do with C is pointers and memory allocation. And it's something that you should definitely cover at some point because of the importance of it. But one of the reasons that I think Python wasn't necessarily the best sole teaching tool actually came up, funnily enough, in Udacity's Introduction to Computer Science. So this is a question that basically asks you to submit a list into a function, and then it increases one number in that list by 1. In this case, 007 becomes 008. And this is the actual code they ended up coming up with. I ran a version of this in class, and for literally the first class, no one got it, surprisingly enough. No one could understand why it was mutating the original list. Eventually someone did get it. This was during the homework period, and it took them 3 hours of Googling to find out why exactly this was the case. Now, I'd like to think that maybe I'm just a bad teacher in some way, but at the same time, I can't really ignore the sheer amount of data I've heard from other people saying that no, this is not normal. This is sort of the way that apparently a lot of people do think, and apparently nearly 50% of all the people who use Python as their first language do have these sort of problems. Hence, we go back to that idea again about how Silicon Valley thinks if you say you're a Python developer to begin with. And, well, I guess I'll actually wrap up because we're nearly almost out of time. So, thank you for this. I hope you found it somewhat interesting. It was severely curtailed, unfortunately, due to my habit of going on. But these are just some thoughts of mine that I hope you've gotten some idea from this. I think that the best sort of curriculum is to try and make some way that you teach in Python to begin with, because that's basically what about half of them, in my experience, are actually there for, is simply to use the computational idea of thinking, the way of programming with another language, like an Excel perhaps, but somewhere else. They want to understand what's going on. They work in other industries. They work in finance. They work in analytics somewhere else. They work in insurance. They work in banks. They work in treasury departments, for example. And they're not there necessarily to learn the idea of how memory works. They're just there to learn, how exactly do we do this operation? How do we get this transformation to happen? And I think a good example in that case is, MIT does use Python as an introduction, but a lot of other courses now use a C section after that as well to deal with more advanced topics. Python is very much the algorithmic way of thinking. It's the introduction to computational thinking, as MIT says in its book. And as I've sort of said there at the C bit, Jesus. Okay, that's a sign. I'll stop now in a moment. Funnily enough, I think there should be another bit as well that encourages people to go beyond it if they are interested, but not necessarily to have such an unstructured environment. I was interested, and when I finished teaching Python, I found there was tons of material online, but there was no guidelines as to what way I should follow, what should I learn next, and what was, how could I compare myself to find out what I was missing. And I think that it would be a good idea somehow in the future to try and make up some sort of course, if at all possible, that would encourage you. You've done Python. Okay, what is the next step for you? Do you understand these concepts? If so, this is what you should ignore and what you should do next. And fully enough, Carnegie Mellon actually in the United States has an introductory course that's in Python, and immediately after that, it has a bit on C and C++ that uses it for far more advanced problems. And I think we should also take this opportunity. I'm just going to wrap it up now to say. Python is a fantastic language for doing all sorts of stuff. It's very practical, it's a great way to reach a mass of people, but I think at the same time we should be thinking, is everything that's embodied by Python something that, is it a way effectively that we should be teaching? Are we missing out on a lot of essentials by simply, choosing a language that's relatively easy rather than one that's perhaps suited better for all the tasks regardless of how ugly it looks? So I'll leave there so you can escape, don't worry. Okay, thank you.